Anywho, good morning, everybody. Welcome back to Calc 2. Plan for today. As promised, I have a quiz for you on Standard 14, and then we're going to jump into Standard 15 on Power Series. My office hours this week are the usual ones for the next few days, 11 to 12 and 1 to 2. Posted new web work yesterday, homework 19, which will be due Friday. Don't forget you also have one due Wednesday. Alright, so here's the game plan. Standard 15, I've decided is the last one I'm going to test you over. So on the sheet I passed out a week ago, listing the number of total masteries you need, go ahead and knock 2 off of all of those totals. So like instead of 32 masteries for an A, you need 30, for instance. That's just, we're only going to get to 30 masteries. But that doesn't mean we won't talk about Standard 16 material on Taylor series. We'll probably get into that in class, I'm guessing, partway through Wednesday and on Friday. But the plan is, Standard 15 will take us about a class and a half to work through, I expect. So we'll have our Standard 15 quiz on Friday. Also, don't forget, maybe I should go ahead and mention this too. We'll have an exam next Monday. Which will, of course, have questions on it from every standard that we've done this semester. Any questions or comments before we get started for today? I'm a little bit behind on grading at the moment. I apologize for that. I'm going to try and get caught back up this afternoon so that everyone's mastery totals are up to date with retests and last Friday's quiz. A medical company figured out one day how to package basic knowledge in pill form. So a student goes to the pharmacy one day, asks what kind of pills are available. Says, oh, I'll have one for English. Pharmacist goes back, gets the student an English pill, sells it to the student takes it, and instantly knows a lot more knowledge about English. Does the same thing for history and chemistry. And then finally, the student's trying to finish out the core requirements, I guess. So it says, do you have any pills for math? Pharmacist groans and says, oh, just wait 1 second, sir. Well, goes in the back, comes out looking an enormous pill. Drops it down on the counter with a thud. The student says, wait, that's the pill for math? It's enormous. Pharmacist replies, you always knew math was a little hard to swallow. And with that, I will pass out today's quiz. So let's see, y'all know the drill. Have fun. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Quizzes in, please. Alrighty, so here we are, the last full week of class. Don't be so excited, Devin, or I'll make it harder on you. So, we got a big plan for this week, which is to tie together the idea of series to functions in terms of x. So here's our goal in the last couple of standards. You all remember back in Calc 1, learning about tangent lines and linearizations to a function? So the idea was we would have a function, something like, I don't know, f of x equals e to the x. And let's say we wanted to find the tangent line at x equals 4. The idea of what we would do in Calc 1 is we would look for a function that's equal to the value of f of x at 4, and that was that had the same slope at 4. Meaning we wanted that if we have a tangent line, call it L of x here, we wanted to find a line L of x satisfying that L of 4 was equal to f of 4, and so that the slope, in other words L prime at 4, is equal to f prime of 4. And that's something you likely saw at some point in your life during Calc 1, is how do you find a tangent line? And the idea is you would do something like f of L of x equals f of 4 plus f prime of 4 times x minus 4. So that was the linearization formula. What we're going to be doing this week, and kind of our last couple standards that we're going to be looking at, is we're going to be talking about, instead of finding a tangent line to a function, how about a tangent parabola, or a tangent cubic function, or a tangent degree 4 polynomial, or, dare I say, a tangent series to our function, which ideally will match up with the value of the function at every single point. So that's going to be taking us into standards 15 and 16, where we're going to be looking at, in standard 15, how can you define a function in terms of a series? And then in standard 16, we'll look at this question of how do we find like sort of a tangent series to a function, which is going to lead us into a discussion of something called a Taylor series. And Taylor's not even here to hear about it. Most disappointing. All right, so standard 15, we're going to be looking at power series. like I said, standard 15 is going to be focused around the idea of how do we define a function in terms of the series, and how do we determine where that function is going to converge or diverge. And the type of functions we're going to be looking at, we're going to call power series. So the main idea behind a power series is you're defining a function like big F of x is going to be some sum from n equals 0, it doesn't have to start at 0, but I'm going to write it starting at 0 to infinity, of some constants times x minus another constant c raised to the nth power. Which, if we sort of write that out, is going to be a function that takes in a value of x, and what the function is going to spit out is going to be an expression of the form a naught plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed, etc., going on forever. And if you try and define a function of x that's defined in this way, we call that a power series. Why power series? I'll be honest with you, I'm not exactly sure where that name originally came from. I'm guessing it's something to do that the fact that you're taking powers of x, that if you were to expand this out, you would get like x and x squared and x cubed, etc., etc. We say that the power series is centered at a value of x equals c. Due to the fact that if you look at each term in this series, you're sort of having different powers of x minus some constant c to each positive power. You're going to have an x minus c term, an x minus c squared term, an x minus c cubed term. And due to that, we say that the power series is centered at that value c. So let's look at an example of one of these things. Let's look at the function. This one left you some space on the first page to make some notes. On the second page, we've got something special in mind planned for this one. I'm going to look at the power series defined by big F of x is going to be sum from n equals 1 to infinity of 2 to the n over n times x minus 5 raised to the nth power. Which, if we start to write out terms, meaning if we start plugging in some values of n and look for a pattern, what we're going to get is a series that looks like 2 over 1 times x minus 5 plus 2 squared over 2 times x minus 5 squared plus 2 cubed over 3 times x minus 5 cubed, etc., going on forever. Which we could simplify a little bit if we wanted to get 2x minus 5 plus 2 times x minus 5 squared plus 8/3 times x minus 5 cubed, and so on. So, question. What is our c value here? In other words, if a power series of this general form is centered at x equals c, what's going to be the value of c in this expression? Where is our power series going to be centered? Would you say, Jonah? So in other words, in a general power series, if all of the terms sort of look like x minus c, constant times x minus c raised to some power, what can we say is our c value here, so that everything in this expression is of the form constant times x minus c raised to a power?
5.
Yeah, exactly. We're going to say the fact that all of our terms are, you could think of as being like powers of x minus 5 times some constant, means that this is going to be a series that is centered at a value of c equal to 5. And that's going to be important later on, knowing how to tell where is your power series going to be centered. So if we look at this series for a second, if I were to drop the plus dot 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 at the end and just leave it with 2 times x minus 5 plus 2 times x minus 5 squared plus 8/3 times x minus 5 cubed, what type of function does that look like? This is a specific type of function that we've seen before, where we're just dealing with like powers of x that are positive integer values of x added together and multiplied by some constants. Anybody remember what we call this type of function? James?
Is it a geometric series?
Well, if I'm dropping the plus dot dot dot, it's not a series.
Oh, geometric then.
We wouldn't normally call that a geometric function. Think back to, oh gosh, what was it? Standard 4, where we said we were looking at rational functions defined in terms of one of these sorts of things divided by another of these sorts of things. Yeah, it would be a polynomial. So one way you can sort of think about how a power series behaves is that a power series is basically an infinite polynomial. Normally when you think of a polynomial, you think of something like little f of x equals, I don't know, 1 plus x squared minus 2x to the 5th. Is something like what a polynomial would look like. The whole idea behind a power series is that you have a polynomial that never ends. It keeps on having more and more positive powers, positive integer powers of x that keep going on forever. And so, given a series like this, what's the question we've been asking, Mary, for the last several standards about series? If I were to give you a series, what have we been looking at? Yeah, whether it converges or diverges. And we're going to be doing the same thing with power series. We're going to be asking the question, if you have a power series, is it going to be a convergent power series, or is it going to be a divergent power series? But with a slight twist to it. Instead of just straight up asking the question, is this power series convergent or divergent? Instead, we're going to be asking a different question. Where the question is, for which values of x will the power series converge, versus for which values of x will it diverge? Because it doesn't make sense to just really take this series in a vacuum and say, does that series converge without specifying some value of x? But we could ask the question, for instance, if I were to give you x equals 5, meaning we were plugging in big F of 5, we're going to get a series of the form sum from n equals 1 to infinity of 2 to the n over n times 5 minus 5 to the n. And we might ask the question, at big F of, when we plug in 5 for x, are we going to get a series that converges or diverges? Rodham, what do you think? If we were to plug in 5 in this series expression everywhere that we see an x, do you think we're going to get a convergent series or a divergent series? Why do you say that?
Because you have 0 in your parentheses, so each term would be multiplied by 0, and then 0 plus 0 is just conversion to 0.
Yeah, if we started writing out terms, we'd get something like 2 times 0 plus 2 times 0 squared plus 8/3 times 0 cubed. Well, you could probably guess by now what's that series going to be. Well, if you add 0 to itself infinitely many times, that's going to be a series that converges to 0. Whereas we can contrast that with, if we wanted to look at a different value of x, like, let's say we wanted to look at x equals 6. Well, if we plugged in big F of 6, what would we get? We'd get a sum from n equals 1 to infinity of 2 to the n over n times 6 minus 5 raised to the nth power. Again, I'm just plugging in 6 for x here, not for n, but for x. And then 6 minus 5, Devin, help me out here. What's 6 minus 5?
1.
If I take 1 to the nth power, what's that going to give me?
1.
If I multiply by 1, what's going to change?
Nothing.
Indeed. So it turns out this x minus 5 to the nth term is just going to become 1 to the n, or we can ignore it entirely. And then this series will become sum from n equals 1 to infinity of 2 to the n over n times 1 to the n, which, as Devin pointed out, the 1 to the n term doesn't actually affect anything, so we don't need to really include it. And then, Kate, would you say this series is a convergent or a divergent series?
Divergent?
Why divergent?
I don't know, I just did a ratio test.
Oh, yeah, you could do a ratio test on that. The other way you could handle that is ask the question, Kate, in general, which of these is going to be bigger, 2 to the n or n? Yeah, 2 to the n is always going to be bigger than n. So if we were to take a fraction of 2 to the n over n, where the numerator is always bigger than the denominator, if the numerator is always bigger than the denominator, can we get a limit of 0 as n goes to infinity? I would say not. If 2 to the n is always bigger than n, there's no way that this fraction can go to 0 if its numerator is bigger than its denominator. So we can say, by the divergence test, this series is going to diverge. You could also do the ratio test on this. Would be another good way to go about determining that. If you tried to find your R value using the ratio test, you would not get an R value less than 1. So what does this imply? Moral of the story here is, for some values of x, we could meaning there's some numbers we can plug in for x up here and get a convergent series. There's other, like 5 for instance. There's other values of x that we could plug in, like plugging in x equals 6, that would give us a divergent series. And so given a power series like this one, the question we're going to be looking at in this standard is not just, here's a single series, determine whether it converges or diverges. We're going to be looking at the question of, here's a power series, what values of x are going to make that power series converge versus what values of x are going to make that power series diverge. Any questions or comments related to that? Alrighty. So let's take a look. So now I'm going to be on the second page for those of you in the packets. So for which values of x will the power series big F of x equals sum from n equals 1 to infinity of 2 to the n over n times x minus 5 to the n converge? It's going to be the question we're looking at on this page. Joy, do you think it would be appropriate, if we want to find all the values of x where this converge, to try plugging in every single real number for x one by one, and then checking all of those series to see if they converge or not? Probably not. That would take a while, as in an infinite amount of time, because we would be plugging in infinitely many values of x. So just plugging in individual numbers for x is probably not going to be super helpful for us. So do we have any way to test a bunch of values of x all at once? Turns out the answer may surprise you. Turns out there is a test that we can do that will make actually checking all values of x sort of all together, or at least most values of x all together, a whole lot easier. And that test is going to be our most recent one from today's quiz, the ratio test. So let's take this series and do the ratio test on it, just to see what we get. And we're going to get some expression in terms of x. So I want to take a limit as n goes to infinity of the n plus first term in this series divided by the nth term in this series. So let's see. Bethany, what's going to be the n plus first term in this series?
N plus first term.
So replacing all of our n's with n plus 1's.
So that would be 2 to the n plus 1 over n plus 1, all multiplied by x minus 5 to the n plus 1.
You got it. Yeah, it's going to be 2 to the n plus 1 over n plus 1 times x minus 5 to the n plus 1. And we're going to be dividing that by the expression we get with just n's. 2 to the n over n times x minus 5 to the n. Which, let's see, if we invert and multiply and sort of combine like terms, what I think we're going to get is something like 2 to the n plus 1 divided by 2 to the n times, let's see, x minus 5 raised to the n plus 1 over x minus 5 raised to the n multiplied by n over n plus 1. Let's see, Katie, what's 2 to the n plus 1 divided by 2 to the n going to be equal to? Yep, first term just comes out to 2. Allie, how about x minus 5 to the n plus 1 over x minus 5 raised to the nth power?
X minus 5.
Yeah, so it'll give us an x minus 5 term. And then Aiden, how about n over n plus 1.
Could we say that simplifies to, well, with the limit, I guess, it would simplify to 1.
Yeah. N over n plus 1 by itself doesn't really simplify at all. But if we took a limit of that as n goes to infinity, we would get a limit of 1. It is true. So we're going to get 2 times x minus 5 times 1 as n goes to infinity, which is the same as 2 absolute value of x minus 5. And question, what needs to be true about this overall limit, this 2 times absolute value of x minus 5, if we wanted our initial power series to be convergent? In order for this series to be convergent, what needs to be true about 2 absolute value of x minus 5? Devin?
It has to be less than 1.
It has to be less than 1. So let's take a look. Let's take a look at a few different cases here. So we know that if r is, so our r value here we can think of as being 2 absolute value of x minus 5. If that's less than 1, we know our series converges. Well, if we try and solve that for x, we'll get something like, we can divide both sides by 2 to get that the absolute value of x minus 5 has to be less than a half in order for our series to converge. All right, Nathan, I have a question for you. I'm going to put it on the sideboard here. If I were to ask you, Nathan, what values of x are going to have an absolute value less than 10? What sort of x values would you say lie in that, are going to satisfy that?
1 through 9.
How about numbers in between?
All of those two.
How about 0?
That one too. Wait, so is everything less than 10?
Everything less than 10? What about negative numbers?
It was everything less than 10 in the absolute value.
True, absolute value of x less than 10 is going to be true if absolute value of x is less than 10.
How do you want me to say it?
How could we just say something about x? You're right that in order for x to be less than 10, we need that, or the absolute value of x to be less than 10, we need that x is less than 10. But what other condition does x need to satisfy in order to have an absolute value less than positive 10? Maybe?
It has to be greater than like -10.
Yeah, we also need x has to be greater than negative 10. Because if I try to give you something like x equals negative 20, true or false, Nathan? Is the absolute value of negative 20 going to be less than 10?
No.
It's not. So not only does x have to be less than 10, it also has to be greater than negative 10 in order to satisfy that. So with that in mind, let's see. Maria, if x minus 5 were to have an absolute value that's less than a half, what does that imply about x minus 5 by itself?
It has to be between negative 1/2 and 1/2.
Bingo. Yeah. Whenever you see something like this, absolute value of expression is less than a number, that means that the expression inside the absolute value has to be between the negative version of that number and the positive version of that number. So let's see. Rhoda, if has to be between negative 1/2 and positive 1/2. What does that tell us about x by itself?
It has to be greater than 5.5 and less than 4.
It has to be greater than 5.5 and less than 4.5.
Yeah.
Uh-oh.
Wait, flip it.
Oh, it has to be less than 5.5 but greater than 4.5.
Yeah.
Yeah, I think that's the one you want. So I'm gonna say, I don't think there is anything that's both greater than 5.5 and less than 4.5 at the same time. Yeah. So the power series, we're gonna say converges for x between 4.5 and 5.5. 4.5 and 5.5, however you want to state that. Which is good, because that kind of matches with what we saw earlier. What we saw earlier is that at x equals 5, we thought that the series should converge, which is good, because 5 is between 4.5 and 5.5. Not the way Rhoda put it, but the way she put it the second time. And at x equals 6, we said the series should diverge. Emerson, is 6 between 4.5 and 5.5? How about that? So in the case where x is strictly between 4.5 and 5.5, we're going to say that the power series is convergent. Although we're not quite done yet, because we still have to consider the other possibilities from the ratio tests. Before we move on to other possibilities from the ratio tests, everyone on board so far? I have a sneeze, it's trying to escape, it's not doing it. So if r is less than 1, we said that the series converged. If our r value, which was 2 times x minus 5, is greater than 1, Joanna, what did we say happens with the ratio test when you get an r value that's greater than 1? Yeah, we get a divergent power series. So that's the same as saying absolute value of x minus 5 is greater than 1/2. And Gabe, what values of x are going to satisfy absolute value of x minus 5 is greater than 1/2? If absolute value of x minus 5 less than 1/2 gave us numbers between 4.5 and 5.5, what would it mean if that absolute value was greater than 1/2 instead of being less than 1/2? What would happen, in other words, if you sort of flip that around?
I think all numbers less than 4.5 and greater than 5.5.
Ah, now we're getting into what Rodin was saying earlier. Slight issue with what you said. I'm going to replace the word and with or, because there's no number that's both of those things, but there are plenty of numbers that are at least that are one of those two things. So yeah, so this is true if x minus 5 is greater than 1/2, i.e. x is greater than 5.5, or if x minus 5 is less than negative 1/2, i.e. x is less than 4.5. So for both of these intervals, we can say that the power series diverges. Neato Dorito. So we know if we plugged in a value of x strictly between 4.5 and 5.5, we would get a convergent power series. Whereas if we plugged in a value of x that was strictly greater than 5.5 or strictly less than 4.5, we're going to get a power series that's divergent. So Nora, what does that leave us with that we still need to check? Because I don't think we've checked all real numbers at this point. What values of x haven't we checked yet, other than values of x strictly between 4.5 and 5.5, values of x strictly greater than 5.5, and values of x strictly less than 4.5?
We haven't checked what happens when we're equal to 4.5 and 5.5.
Yeah, we still have to check what happens at x equals 4.5 or x equals 5.5. And those are going to be the points we get when we set our r value here equal to 1 instead of being greater than or less than 1. So let's do that. If r equals 2 absolute value of x minus 5 is equal to 1, well, that's going to be the same as saying absolute value of x minus 5 is equal to 1/2, which is the same as saying x minus 5 is either equal to 1/2 or x minus 5 is equal to negative 1/2. So this will give us x equals 5.5. This will give us x equals 4.5. And Carson, why did you have to call on me? Such exasperation. Why did the ratio test tell us happens when we get an r value equal to 1? It's inconclusive. So in this case, we get ratio test is inconclusive. Put a big sad face. The ratio test tells us exactly what happens if x is strictly between 4.5 and 5.5, or if x is greater than 5.5 or less than 4.5. But unfortunately, at these 2 points where we get an r value of exactly 1, ratio test doesn't tell us anything. That was sort of the inconclusive case, which is a bummer. So how can we tell what happens at 4.5 and 5.5 if the ratio test doesn't tell us anything? Aiden?
Could we plug in or inconclusive values like 5.5 in for x, and then we can solve by other rules that we use?
I think that's a great idea. Yeah. Back at the start of this problem, when we asked the question, should we just try plugging in numbers and check every single number to see do we get a convergent or divergent power series like we did with 5 and 6 at the start, Joyce said that would probably be a bad idea because we'd be plugging in infinitely many numbers to have to check. But now we've kind of gotten down to only having 2 more numbers to check. And with only 2 more cases to check, as Aiden pointed out, those are ones we could just plug in, find out what happens when we plug in 4.5 and 5.5 into, I seem to have lost the original series, but I'm sure it'll show up somewhere on the board. So let's do that. Do that here. Hey Nolan, which one do you want to start with, 4.5 or 5.5?
4.5.
All right, Nolan wants to start with 4.5. So if x equals 4.5, then when we plug in f of 4.5, we're going to get, what's the series again? Oh yeah, it's going to be sum from n equals 1 to infinity of 2 to the n over n times 4.5 minus 5 raised to the nth power, which is the same as sum from n equals 1 to infinity of 2 to the n over n times, what's that, negative 1/2 raised to the nth power. Phoebe, is there anything here that we can kind of simplify, make this series easier to look at / work with? Specifically, can we combine our 2 to the n and our negative 1/2 to the n terms somehow?
Probably.
Answer is yes, we absolutely can. Bethany, how would you do that?
So you could put -1 to the n in the numerator, all divided by 2 to the n in the denominator of that fraction.
Yeah, we could when you have two different bases raised to the same exponent that you're multiplying together, you could just multiply the bases to that power of the exponent, take 2 times -1/2 to the n over n, which is going to give us sum from n equals 1 to infinity of -1 to the n all over n. That series looks vaguely familiar. Hey Jonah, where have we seen this before?
It's just the. It's not a geometric series.
Nope.
Or the last standard.
It's two standards ago.
Which was.
If we had 1 over n, we called it the harmonic series.
Right.
So what did we call it when we had this -1 to the n over n? When we took our harmonic series and made it, I don't know.
It's like alternating series.
Yeah, it's an alternating harmonic series. And Caleb, refresh my memory. Did we say that the alternating harmonic series converged or diverged?
Diverged. Converged.
Huh? It's an alternating series where the individual terms are going to 0. So what does the alternating series test tell us our series should do? Megan?
Converge.
Yeah. Turns out this one is convergent. Because it's an alternating series where the individual terms go to 0, so we can use the alternating series test to say, hey, this power series here, well, this isn't a power series, this alternating harmonic series has to be convergent. Bethany?
Does it make a difference whether it's like absolutely convergent or just conditionally convergent or not? Because
It'll make a difference here in a minute when we check x equals 5.5 and suddenly it becomes the regular harmonic series, but that'll be, that'll come into play a minute from now. So at x equals 4.5, turns out our power series is going to be convergent. If we look at x equals 5.5, we take f of 5.5, we'll get sum from n equals 1 to infinity of 2 to the n over n times 5.5 minus 5 raised to the nth power, which is the sum from n equals 1 to infinity of 2 to the n over n times 1/2, positive 1/2 this time, raised to the nth power. Kate, how can we simplify this series down a little bit?
Just do 2 times 1/2 all raised to the n over n.
Yeah. We could combine our 2 to the n and 1/2 to the n to get 2 times 1/2 to the n over n, which is just going to be sub from n equals 1 to infinity of 1 to the n over n. And as Devin pointed out earlier, 1 to the n is just 1, so this comes out to 1 over n. And then Nathan. Here we have the regular harmonic series. Is that going to converge or diverge? It's going to converge, why?
Because
the individual terms are. Does that mean the sum has to be? From the fact I'm asking that question? Well, this is actually a p-series with p equal to 1. And what do we know about p-series if p is equal to 1? It's going to have to be divergent, actually. Because you could write this as 1 over n to the first power, and that's as a p-series with p less than or equal to 1. If p is less than or equal to 1, we said that a p-series diverges. If p is strictly greater than 1, we said that it converges. So, Bethany, you asked the question earlier, does it matter if it's conditionally versus absolute convergent? It actually does matter, because the fact that it's only conditionally convergent means that our power series is going to converge at 4.5, but not at 5.5. If this had been absolutely convergent, like if it had been -1 to the n over n squared here, for instance, then we would have gotten that it converged at both 4.5 and 5.5, which wasn't what happened. Does that make sense? So, what's our grand final answer? So y'all are probably running out of room, but we're about to be done here, on this page at least. Is that big F of x, which is the sum from n equals 1 to infinity of 2 to the n over n times x minus 5 to the n converges if x is between 4.5 and 5.5, including 4.5, but not including 5.5. And those are the values of x that we can plug into our power series and get a convergent series out of it, as opposed to one that diverges.
Is it just then assumed that every other value is divergent when you say that?
Say what?
Is it assumed that every other x value is divergent when you just state?
Yes. If you really wanted to be precise about it, put in 2f's, which is shorthand for if and only if. And if and only if means that if x is in this interval, then it converges. If x is not in this interval, then it must diverge. Let's take a look at this interval for us real quick. By the way, this is kind of the general process you always have to go through in order to determine where your power series converges or diverges, is you use the ratio test to get something like, in this case, 2 absolute value of x minus 5. You find what values of x are going to make that strictly less than 1. And then you have to kind of check the two endpoints of that interval manually, like what we did here, well, what we did over there at 5.5 and what we did a second ago at 4.5. You kind of have to check those individually because those are where the ratio test comes out to 1 and doesn't tell us anything. Let's take a quick look though at a graph of this interval. So we have 4.5 and 5.5. We said that the power series converges in the interval from 4.5 to 5.5, including at 4.5, not including 5.5. And then outside of this interval, it diverges. Emerson, what number lies in the middle of this, smack dab in the middle of this interval over which it converges? Yeah, halfway between 4.5 and 5.5 is going to be at x equals 5. Sarah, what significance does 5 have to our power series? We said at the very beginning of looking at this series that 5 has a special meaning for this series. What was it?
So because if you plug it in, it equals 0.
Yeah. And so we said that 5 was the what of this power series? Looking back at the first page. Oh wow, it's snowing outside. Aren't you all excited for summer break? Yeah, the center of the power series. So it turns out that when we say something like 5 is the center of the power series, the reason why we call it the center is because that's always going to be the center of the interval over which the power series converges. So the interval over which big F of x converges is going to be centered at x equals 5. And it turns out any power series is always going to behave something like this, let's see, where you have some interval centered at the center of your power series over which the power series converges, and everywhere outside of that interval, the power series is going to be divergent. We'll talk a little bit more about the theory and do a couple more examples, though, in class on Wednesday. But with that, that's essentially the big idea behind Standard 15, is using the ratio test to determine, for a power series, where does it converge versus diverge. Homework 19 has a few questions about power series and finding where they converge or diverge. Encourage you to check that out. I'll see you all on Wednesday.
We have a quiz on Friday.
Correct. Yeah, no quiz this Wednesday, but we will have a Standard 15 quiz on Friday.